Alright, welcome everybody. We're going to take a look at how to solve a plane stress problem using FEA 2D solver. Here on the left hand side of the screen is where we have our example problem of a plane stress system constrained on the left hand side with a pressure load on the right hand side. So we'll go ahead and look to the right side of our screen, which is where we have the Excel input file for this problem. And we'll just go tab by tab, so we'll start off with the nodes. We know that we have 9 nodes, so we'll just go ahead and enter in all the 9 nodes that we have. And I'm just going to go ahead and choose that the origin of the coordinate system starts at node 1. It can start wherever you want. I'm going to choose node 1. And I think for units, we'll just try newtons and meters. So baseline newtons for force, meters for units of length, pascals for pressure. We'll start from there. So we're going to adjust everything that we have in terms of our units on this side to be in our baseline units that we just described. Newtons, meters, and pascals. Okay, going back to node 2, that means that we are 0.2 meters over and 0 in the y direction, and that we are 0.4 meters over for node 3, still 0 in the y direction. Okay, let's go ahead and copy that because it's the same x location for nodes 4, 5, 6, and 7, 8, 9. And then we also know that 4, 5, 6 are going to be 0.2 meters up, so we'll go ahead and do that. And 7, 8, 9 are going to be 0.4 meters up. Okay, we won't worry about the node angle because the node angle doesn't matter in this problem. We don't have constraints that are in off-axis. These constraints are nice in that they are only in the vertical, only in the horizontal direction at nodes 1 and 7, both x and y directions for node 4. No need for a node angle in this problem. Okay, we'll go ahead and move on. We don't have any line elements in this problem. We could, but we don't. We could have spring elements, but we don't. But we do have triangle elements, and so let's go ahead and enter those in. We have elements 1 and 2 as our triangle elements. And with our triangle elements, the main thing that we want to be careful of is to enter in our nodes in clockwise order. Pardon me, counterclockwise order. Oh my gosh. Counterclockwise order. Look at the arrow. There we go. Counterclockwise order. So we can start with any node we want. So I'll go ahead and start with node 4. Why not? But this means that the next one has to be node 1 and the next one has to be node 5. Similarly, for element 3, I can start with node 5 just randomly. But if I start with node 5, the next one has to be node 1 and the next one has to be node 2. Okay, moving on to our elastic modulus. 70 gigapascals means that it will correspond to 70 times 10 to the 9th pascals. For a Poisson's ratio, we have 0.3. For a thickness of 5 millimeters, corresponds to 0.005 meters. No thermal stuff in this problem, so we just won't worry about it. All right, we'll go ahead and bring that down, and that should be everything we have for our triangular elements. I'm going to go ahead and copy this as we move to our quadrilateral elements because our material properties are going to be the same. So we'll just go ahead and keep that there. In fact, I'll go ahead and highlight this last row and drag it down one more since we do have 3 quadrilateral elements. Alright, moving on over, we have element 3, 4, and 5. And still we have to be careful about, with all these plane stress elements, that we have this counterclockwise ordering. And that's true for plane stress elements, and then if you start learning about 3-dimensional elements, there's a specific node order expectation that the solver will expect. And so it's true with everything, but with our plane stress elements, it just needs to be counterclockwise. So we'll go ahead and start with element 3. Starting with node 2, 2, 3, 6, and 5. Going to element 4, we have 5, 6, 9, and 8. Going to element 5, we have 4, 5, 8, and 7. And that should be everything that we have for our quadrilateral elements. So we can continue moving on. Next tab, temperature. There's no temperature change in this problem, so we'll go ahead and ignore that. We have some constraints though, so we'll go ahead and look at node 1, only constrained in the x direction, so we'll just put degree of freedom 1 there. We have node 4 that is constrained in both the x and the y directions. And we have node 7 that is only constrained in the x direction. Great, all done with our constraints. Node loads, well, we don't have that in this problem. We just have a pressure load. So since we just have a pressure load and no loads forces or moments specifically applied to nodes, we will not worry about it. Similarly, we do not have a distributed load because that is usually geared towards beam elements, line elements, and we don't have that in this problem. We have plane stress elements, or planar elements, and so instead we will move on to our pressure loads. Alright, so when we describe our pressure load, we have to describe the magnitude of the pressure load, and we have to describe the elements and the nodes that that pressure load is prescribed to. So for example, if I go to element ID 3, where we do have a pressure load, it is in the horizontal direction. I'll just go ahead and put it 0 there. It could be in another direction. It could be 90 degrees. In that case, it would be a purely traction load, right? But in this case, it is orthogonal to it, so we'll go ahead and put 0 as the angle. Alright, we have to enter the pressure twice, 2 megapascals. That corresponds to 2 times 10 to the 6th pascals. And we're going to put that same value on both nodes. Now, keep in mind the reason that it asks for it at both nodes is because we could have a triangle, right? Like what if we had something like this, right? In that case, we'd have a smaller amount of nodal force that would eventually get, it all gets translated back into nodal forces, right? In plane stress elements, the nodes actually don't have any rotational stiffness, so there wouldn't be a moment associated with it. But yeah, at nodes 3 and node 6, it would translate that pressure into forces at those nodes, right? So it could be different, but in this case, they're the same. So we'll have the same pressure described here twice, and then we'll go ahead and enter in that the first node it occurs on is node 3, the second one is node 6. Now that's important because we want to be able to describe that this is the face that it's acting on. Okay, we'll do the same thing for element 4. Element 4, the pressure is still at a 0 angle, and we still have 2 times 10 to the 6th is our pressure load. Whoops. And in this case, we want to describe that face between node 6 and node 9. And with that, my friends, I think we are done with the setup. We'll go ahead and save it. We'll go ahead and close it. And now we'll go ahead and take a look at what happens when we try to run it in FEA 2D Solver. So here we actually already have everything set up. We have the location of the folder where the FEA 2D Solver code is stored. And we also have the location of the Excel input file, or the name of the Excel input file right there. Alright, so we're going to go ahead and look to make sure that all our inputs are what we want. We do want units of length being meters. We want our units of force to be newtons. Temperature can be whatever we want. We don't have temperature in this problem. And we do want text file. We do want graphical plots. We do want element numbers on those plots. We do want node numbers on those plots. There's only a few, so it's nice to be able to reference what's happening. And with that, let's go ahead and click run and see what happens. Alright, good. We got some results. We got a text file, and we got some output. And my goodness, that looks a lot like a beam problem and not the plane stress problem. Alright, FEA 2D Solver does this. I don't know if this is just a bug that happens with the live scripts, but we're going to go ahead and click this, open in the figure window, and then voila, like magic, that's like what we actually want to happen. Okay, I don't know why that happens that way, but that's just what happens. Okay, so here we have the deformation just as we expect. It does vary pretty much linearly across the horizontal direction, so that looks about right. We'll go ahead and scroll down to another problem here. There we go. No figure there, but magically there is one here. I apologize that I don't know why that is. It just happens to be what we see. We see that the von Mises stress results is 2 times 10 to the 6th pascals, or 2 megapascals, and my goodness, that's exactly what we would expect, because we see that we have this pressure load applied. We have the constraints here such that this node and this node can go ahead and roll in towards node 4 to do that Poisson effect, right? As it's getting pulled this way, it kind of becomes a little bit more narrow. And so it should be, throughout this whole structure, it has a stress of 2 megapascals. That's exactly what we're seeing, so that makes sense. Alright, let's go ahead and look at the next result that we have. Once again, in the live script, for some reason it's showing the beam. Don't worry about that beam. Go ahead and move up here. This shows us the quality contour results, and what it's using is the minimum Jacobian ratio. And Jacobian is just a the Jacobian matrix is used in the formulation of isoparametric elements, but you can also take the determinant of Jacobian at different nodes, take the ratio of those, whatever the minimum ratio, it kind of gives you an idea of what that quality of those elements should be. In this case, we have perfect squares, so it's perfect in all those elements. You'll notice that it does not exist for those triangular elements because, well, they're triangular, they're not quadrilateral elements. Alright, so those are all of our graphical results. Let's go ahead and take a look at our text file results that popped up. So we had this plane stress problem here, and it should have popped up with a text file. So let's go ahead and click up here and click back. Maybe then it will have it. And there it is. Okay, our units are as expected. Our total applied load is as expected. Now, keep in mind that we did apply a pressure load of 2 megapascals, but we applied that pressure load over an area of 400 millimeters multiplied by 5 millimeters, and so what we're looking at is a cross-sectional area of 2,000 millimeters squared. So if we multiply 2 megapascals by 2,000 millimeters squared, in other words, it's kind of like 2 pascals pardon me, 2 newtons per millimeter squared, and so that means we should get 4,000 newtons, and that's what we got. So we have a total applied load of 4,000 newtons, and fortunately our total reacted load is exactly the same with some numerical error here, and we can go ahead and check to see what our displacements are, and as expected, most of our displacements are occurring in the y direction when we look at node 2, for instance, but we also look at this, we have some Poisson effect where node 2, that's this one, is kind of moving up, right? We see nodes 1, 2, and 3 all moving up. We see very little movement in nodes 4, 5, and 6. Let's go ahead and make this a little bit bigger so we can kind of compare right adjacent to each other. Very little movement in the y direction there, and we have nodes 7, 8, 9 moving downward a little bit. So that's just as expected as well. There we go. Here's how our pressure load got distributed amongst the nodes, just as expected, right? We'd expect node 6 to take double the amount of nodes 3 and 9, right? Because if you look at the actual area that node 6 has, right, if you split the elements in two, we got that much going to node 6, we only have half of an element going to node 3 and half of an element going to node 9, so that makes sense. And if we go ahead and look at our reacted loads, we see a bunch of pretty much numerical error, but we see nodes 1, 4, and 7 taking the brunt, so perfect. And if we look at our stress results, sure enough, we see stress primarily in the x direction with just some numerical error elsewise. And we can also take a look at some of those stresses that are calculated off the baseline stresses, so max normal or principal stress, right? Minimum normal stress. We have a maximum shear if we rotate our perspective of the stress element. We have a von Mises stress. So all those look well and good, and that's about the same that we have for our quadrilateral element as well. Alright, so that gives us an idea of what's happening in the text results, and once again, if you like, you can always jump down over here and you can kind of check some of your nodal results, or you can check some of your elemental results here if you like as well within the structures contained in the workspace. So if you wanted to, you go ahead and look in the quadrilateral element, you can check your quality, you can check von Mises stress, and you'll notice we have different values, right? We have von Mises stress at the Gauss points, von Mises stress at the nodes. So this is pretty advanced stuff, but through anything with any of these problems, we can search through the workspace and kind of find out the details that went into it. All right, with that, I think we have this problem covered. Okay, thanks everybody.